Welcome to the Performance Improvement Using HLS Pragmas with AMD Vitis HLS Code Analyzer Tech Module. Here is the agenda for this tech module. We will focus on the HLS component development flow in the Vitis Unified IDE, introducing the Vitis HLS Code Analyzer tool, how to get started with the Vitis HLS Code Analyzer, going through an example of how to improve performance using Vitis HLS Pragmas. The Vitis Unified IDE is built on the open-source Eclipse Theia framework, providing a robust and extensible foundation. The IDE is a refresh to merge the GUI layers while keeping the backend flow and functionality untouched. It is an update on the three former tools, Vitis IDE, Vitis Analyzer, and Vitis HLS, integrating them into a single unified environment and merging the different compilers, analyzers, and debuggers into a single tool. It is highly customizable, offers a more responsive user interface, and supports parallel builds, enhancing productivity. It provides a complete HLS development flow, from design entry to synthesis and implementation, and includes core HLS features, making it a powerful tool for hardware-software co-design. Existing HLS Classic projects can easily be imported into the new IDE, ensuring a smooth transition. In the AMD Vitis Unified IDE, HLS components transform C or C++ functions into RTL code, enabling implementation within the programmable logic regions of Versal Adaptive SoCs, Zynq UltraScale Plus MPSoCs, and other AMD FPGA devices. These components are tightly integrated with both the Vivado Design Suite for synthesis, placement, and routing, and the Vitis Unified IDE for heterogeneous system-level design and application acceleration. An HLS component can be used to develop and export Vivado IP to be integrated into hardware designs using the Vivado Design Suite and used with provided software drivers for application development in embedded systems. Vitis kernels for use in the Vitis Application Acceleration Development Flow, for use with AI engine graph applications in heterogeneous compute systems, or for use in data center acceleration. The Vitis Unified IDE and V++ Common Command Line provide the ability to create an HLS component using bottom-up design techniques to ensure that the component meets design requirements before integrating it with other elements into a system design. Here are the steps for developing an HLS component from a C++ function. Architect the C++ algorithm based on design principles. Verify the logic of the C++ code with a C++ test bench. Analyze the performance, parallelism, and legality of the C++ code. Generate the RTL from the source code using the V++ compiler. Verify the generated RTL code using the C++ test bench and RTL logic simulation. Review the HLS synthesis reports and repeat any previous steps until performance goals are met. Package the synthesized HLS component for either the Vitis Acceleration or Vivado IP flow targets. In the Vitis Unified IDE, utilizing the HLS compiler's analysis and productivity features requires a license. The HLS Code Analyzer feature will be available only under this new HLS license. This license can be acquired free of cost and supports both floating and node-locked licensing models. To obtain a license, visit the License Solutions Center. Upon acquiring a license, you'll be able to fully leverage the features shown here within the Vitis Unified IDE. The HLS optimization methodology involves both macro-level and micro-level optimization. Macro-level optimization focuses on the high-level design, while micro-level optimization deals with the lower-level implementation details. The designer needs to create the high-level architecture of the algorithm in C++, carefully considering the design intent and its interaction with the external world. The HLS tool also requires design constraints, such as clock period and performance targets. By leveraging the defined high-level architecture of your CC++ algorithm, Vitis HLS empowers you to generate diverse RTL solutions. This flexibility allows you to explore a wide range of trade-offs between performance and area, ultimately allowing you to select the implementation that best aligns with your application's specific requirements. To facilitate this exploration, the Vitis HLS Code Analyzer offers invaluable insights. It visualizes opportunities for task-level parallelism and highlights the architectural modifications necessary to optimize performance. With this knowledge, you can make informed decisions to refine your design and achieve optimal results. Microarchitecture designs, like creating the state machine, the data path, or register pipelines, are not needed at a high level. These details can be left to the HLS tool, and optimized RTL can be generated by providing design constraints. To allow for optimal performance and area utilization in your hardware designs, Vitis HLS offers a variety of optimization pragmas, such as pipeline, unroll, and array partition. By strategically applying these pragmas, you can fine-tune your microarchitecture to meet specific goals. By combining these optimization techniques, Vitis HLS enables developers to create efficient and high-performance hardware implementations from their software designs. Typically, a program written in C/C++ is executed sequentially on the CPU as shown in this example. In order to achieve high-performance hardware, the HLS tool must infer parallelism from sequential code and exploit it to achieve greater performance. But this is not an easy problem to solve. Task-level parallelism can be applied to the same example as shown here, thereby increasing performance and utilization efficiency. Here, the throughput is improved because it is limited by the maximum latency among all tasks, rather than by the sum of their latencies. This generally means that at a bare minimum, such software needs to be examined for non-synthesizable constructs, and the code needs to be refactored to make it synthesizable. Using the abstract parallel programming model as a basis, two types of task-level parallelism models can be used to structure and design an application, either data-driven or control-driven, or a mix of data-driven and control-driven tasks in a single design. The main differences between these two models are the following. If an application requires some interaction with external memory, and there are data dependencies between the tasks that execute in parallel, then the control-driven TLP model is the best fit. Vitis HLS will infer the parallelism between tasks and create the right channels such that these functions can be overlapped during execution. The control-driven TLP model is also known as data flow optimization in Vitis HLS. In this model, the tool-inferred parallelism can be observed only after co-simulation is run. If applications are purely data-driven and do not require any interaction with external memory and the functions can execute in parallel with no data dependencies, then the data-driven TLP model is the best fit. You can design a purely data-driven model that is always running, requires no control, and reacts only to data. In this model, the tool-inferred parallelism can be observed in C simulation. These two models can be used independently or together, mixing data-driven and control-driven tasks in a single design to achieve efficient task-level parallel code. This table highlights various factors of an HLS design that can be used to decide whether to use control-driven task-level parallelism or data-driven task-level parallelism. Here, you can see that the two forms of task-level parallelism presented have different use cases and advantages. Task-level parallelism is crucial for achieving high performance in modern computing systems.
Coarse-grained design optimization involves breaking down a problem into independent tasks that can be executed concurrently. TLP parallelization is a mental process that requires identifying tasks, analyzing dependencies, and estimating performance. Code analyzers can assist in this process by identifying potential parallelism opportunities and providing performance metrics.
To assist you with this effort, Vitis HLS Code Analyzer provides features that let you visualize the potential for task-level parallelism and understand the architectural changes needed to optimize performance. Code Analyzer will be available only under the new HLS license. Features of Vitis Code Analyzer include data flow graph extraction, performance metrics, performance guidance, graph transformations. The Code Analyzer report extracts a data flow graph in which top-level statements become data flow processes, or DFG nodes, and the data dependencies of these processes become data flow channels, or DFG edges. The graph can be generated from a function or loop body even when they are not in a data flow, helping you better determine how the code might be rewritten in a data flow form. Performance metrics such as the volume of data, transaction intervals, and throughput are determined by Code Analyzer. The volume and access mode of data can be determined from the C test bench based on profiling information. For example, the tool can determine that variable C infers a port 32 bits wide and 8 kilobits of data is written by process 2 before being read. Analyzing the design prior to synthesis, Code Analyzer estimates the transaction interval, or the time it takes for data transfer to complete, and the throughput of the channel. However, because the estimate occurs prior to synthesis, it is less accurate than when calculated from the performance of the synthesized RTL. Code Analyzer helps you identify any major performance blockers the HLS component source code might have. These blockers include cyclic dependencies and memory port contention. Performance guidance helps you understand code structures that might limit design performance and helps identify which metrics can help you understand the level of performance your design can achieve. Based on the data flow graph decomposition and the measured and estimated metrics, you might determine that the graph is not ideal as shown. You can modify the graph by merging processes to perform what-if type design exploration. When the graph is modified, new performance metrics will be determined from the new architecture. Iterations of this design process could result in a blueprint for an ideally architected solution, which you can use as the basis for refactoring your source code. To start a design, you need to understand the HLS component source code in depth to identify its main processes and their dependencies. Vitis HLS Code Analyzer helps you visualize your code as a data flow graph. You can run Code Analyzer as part of the C simulation step. To enable Code Analyzer, select the desired HLS component in the Vitis Components window, hover over C Simulation in the Flow window, and click the gear icon to open the HLS configuration file and the C Simulation settings. From here, enable the Code Analyzer option. After running C Simulation with Code Analyzer enabled, a generated report can be viewed in the Vitis Unified IDE, either in the Analysis view or under the Reports header of the C Simulation step. The Code Analyzer report initially displays a graph of the processes and channels defined by the top-level function of the component. Within the Processes section, the graph's processes are displayed, accompanied by estimated pre-synthesis transaction intervals, TIs, and any design guidance generated by the analysis. The Channels section presents data flow channels entering and exiting each process in distinct rows. Channels are named after their defining variables, accompanied by details such as bit width, anticipated data volume, expected throughput, access mode, and associated producer and consumer tasks, also known as processes. The transaction interval reported in the process section is the minimum delay between consecutive process executions. It is important to remember that Code Analyzer operates under the assumption of independent process execution within the top-level region. Consequently, the region's performance is constrained by the slowest process, which corresponds to the process exhibiting the largest estimated TI and is highlighted in red. Red indicates problem areas of the design. However, note that the pre-synthesis estimates used in the graph do not offer the same fidelity as the post-synthesis or post-implementation metrics.
Code Analyzer can help identify legality issues in data flow designs, improve performance without requiring HLS synthesis, and provide estimates of channel throughput. In summary, Code Analyzer is a valuable tool for quickly assessing performance potential, identifying problems, and resolving them. However, for situations that demand more precise information, synthesis and implementation should be employed. Now that we've looked into the HLS Code Analyzer tool, let's see how we can improve performance using HLS pragmas by using an example design. This example, based on the Beamformer IP, demonstrates micro-optimization techniques to boost performance in Vitis HLS designs. We'll go into the analysis tools and techniques for optimization, focusing on the compute engine portion of the Beamformer algorithm to simplify the example. The fundamental HLS pragmas used for micro-optimization include the pipeline, unroll, and array reshape or array partition pragmas. A high-level block overview of the receiver beamforming concept is shown here. Our example design here implements the compute engine portion of the beamformer with 16 receiver channels, each of which has both a real and an imaginary component. In addition, the beamformer has 3 beams. The design is then optimized to meet a performance specification and synthesized for use on a Versal Premium Series adaptive SoC. It takes 2 primary inputs. RX, I, and Q, sample channel, represents the raw signal data received from multiple sensors or channels for each sample. W, I, and Q, beam channel, are adaptive weights that steer the beam towards the desired direction. They are adjusted periodically, typically every pulse repetition interval. The output is the beam I and Q, sample, beam. This represents the processed signal, focused on the desired direction, for each sample and beam. Here's how it works. For signal reception, raw signal data is captured from multiple sensors and stored in RX, I, and Q. For the beamforming, for each sample, the adaptive weights, W, I, and Q, are applied to the corresponding received signals, RX, I, and Q. The weighted signals from all channels are then summed together to form a focused beam. The resulting focused beam is output as beam I and Q. We want to implement a beamformer compute engine with 16 receiver channels, real and imaginary components, 3 beams, and 2,500 samples per pulse repetition interval. The design goal is to process a PRI of 2,500 samples within 9 microseconds. At a 3 nanosecond clock period, or approximately 333.3 megahertz, this calculates to a maximum interval of 3,000 clock cycles. The loop bounds of loop L1 in the code indicate 2,500 iterations, with each iteration taking 2 clock cycles. Thus, the loop interval will take a minimum of 5,000 clock cycles. Therefore, in this loop, each iteration must be able to execute in the very next clock cycle after the previous iteration. So, the strategy for achieving the specified performance will be to apply a pipeline II equals 1 pragma to loop 1 and then ensure that the HLSC synthesizer is able to meet the requested initiation interval.
The optimization process involves creating a non-optimized sequential version as a baseline reference point, applying the pipeline pragma to the outer loop and observing the automatic unrolling of the inner loops, using the Vitis HLS analysis views to identify bottlenecks, and applying array reshape or array partition pragmas to further optimize data movement. Before optimizing, it's helpful to establish a baseline performance. We can verify functionality with a functional simulation and assess the initial performance to gauge the optimization potential. By default, Vitis HLS applies optimizations for a balance of performance and resource utilization. To disable all optimizations before C-synthesis, turn off the HLS pipeline pragma for loops L1, L2, and L3. This will result in sequential operation, providing the total latency as shown here. Let's now optimize the design using Vitis HLS pragmas. By pipelining the outer loop L1 with the pipeline pragma, Vitis HLS automatically infers an unroll directive for the inner loops L2 and L3. This significantly reduces the total latency. However, due to insufficient data ports, the initiation interval is limited to 16. We found that satisfying the II equals 1 constraint from the pipeline pragma requires 16 loads per clock cycle. Vitis HLS guidance suggests reading all addresses of the second dimension, channels, of the RX sample channels array in a single clock cycle. To achieve this, we must increase the interface size. By default, the interface size matches the data type, 32-bit float. To read multiple floats per clock cycle, we can use either array reshape or array partition. These pragmas widen or duplicate the interface respectively. In this case, we'll use array reshape on the second dimension. This further reduces total latency, and the II is reduced to 3. The Vitis HLS guidance for II equals 3 points to the beams-O beams channels operation, which requires multiple store operations due to the unrolled loop. Applying array reshape to beams-O with dimension 2 reduces the II to 1 and the total latency to less than 3000.